Ačiū. Tai visų pirma, ačiū organizatoriams, kurie pakvietė. Kadangi jau žadėjau kalbėsiu angliškai, tai taip matyti ir darysiu. A little bit about myself. I graduated from Vilnius University, and then I went to Imperial College London, where I did my PhD, mainly on fluorescence lifetime imaging and STED microscopy. So we could achieve like 30 nanometer resolution, like an order of magnitude of improvement over confocal microscopy. So this is on fluorescent beads. It also works well on cells. You can see a STED beam being switched on. So instead of confocal microscope image, you get STED image. Our main achievement there was fluorescence lifetime imaging, recorded with sub-diffraction resolution. So we demonstrated that film can be combined with STED, and also at that time we also demonstrated that by rejecting early arriving photons we could improve STED resolution even further. In fact, even some microscopes, commercial microscopes, utilize that principle nowadays. Then I went on doing optical coherence tomography, and this is what I'm doing still today. So OCT is an interferometric technique. So you have a Michelson interferometer here. You have a laser, broadband laser usually. You have a sample in one of the arms. And a beam splitter splits into the two and recombines the light and sends on the detector. And what happens if the path lengths between the two arms are equal within the coherence length of the laser, you'll have interference. Now, if you move the mirror, you will record an interferogram like this, and each peak of that will correspond to a mirror position. So you can extract the envelope of this, and this is basically an image or a depth information in one pixel of your image. What we use is a camera instead of a point detector to kind of to speed up the process of end-fast image acquisition. And we also put high NA objectives to achieve a higher resolution. Then what you do, you basically send collimated light onto the sample, and you can use any light source. You don't need lasers now. So you detect scattered light, and it interferes on the camera with the reference beam, and what the camera sees is this small interference variation on a huge background. Because what we did here, we don't use pinhole as OCT people do, and we heard from Rimas this morning as well. So the disadvantage of that is we get a lot of backscattered light, which is multiply scattered, and it's not interfering on the camera, and we need to get rid of that. So the way we do is we acquire a few images with a different phase shift in between. So we shift the piezo and record different holograms at each position, and we reconstruct the final image in a similar way like a structural illumination microscopy does, as we heard of this morning. It enables us to acquire end-fast images with any light source, literally, and with a very high resolution. Not as high as in STED microscopy, but relatively high compared to any other OCT system. Thanks to this high resolution, what we can do is acquire images of such quality. So this is 3D data, basically images acquired at different steps by moving sample. And the resolution is so good that it compares to histology slide resolution, necessary resolution for inspecting histology slides. So in principle, we could replace histology procedure, which is very time consuming, because you have to label and you have to look under the microscope and so on, and you have to take it out of the body in the first place. So this would be a more convenient way of doing it. This is structural illumination microscopy that we heard this morning, because we can easily implement this in our microscope, and it's quite useful. So basically, we put a grid in an illumination path, and we image it on a sample, acquire a few images, and reconstruct the optically sectioned image. So now we pop back the objective, and we have reflectance images and fluorescence images, both optically sectioned. So for example, we can acquire 3D data like this, resolved in that direction. For example, if we look at this specific data set from the side, these are axial images, we can see that OCT images and fluorescence images, they are complementary. But again, if we compare to histology slide, we see that there's quite a good match. So again, proving that OCT can replace, or this particular version of OCT, full field OCT, can replace histology. Here's a more practical example. We were looking at neurons in human gut. There are many different reasons why you want to do this. But we wanted to make sure that these are neurons, actually. So we did some fluorescent staining, and again, with this dual modality, we were able to confirm that what we see is actually neurons. And this has, or could have, some practical applications, because now you can imagine an instrument that goes through the tissue and images neurons with high enough resolution to detect them. Whereas H&E slide is usually coming like this, very inconvenient. At a different orientation, you would have to take 50 biopsies like this to be able to tell anything about neurons there. So these were just examples of what we can do with a high-resolution OCT system. Another application that I'm currently working is subsurface fingerprint imaging, quite different application. We have a larger field of view because we need to capture entire fingerprint, but we use this ability to acquire and fast images. And there are many reasons why you want to do this in depth, because surface is not reliable. For example, if finger has some disease, is dirty or bad, you will generate poor quality fingerprint image. So if you look at the cross-sectional image acquired with OCT, you will see an external fingerprint, and then you'll see something very similar a little bit below, like 1 millimeter or less below the skin surface. So it means that we can perhaps try to image this layer when the surface is damaged. And if you look at the histology, again, this is actually the stratum spinosum layer, which generates most of OCT signal, and below is dermis-epidermis junction, from which external fingerprint regrows in case of its damage. There are some other subsurface imaging techniques used in fingerprint imaging in biometrics, including iPhones. They all claim that they could see just below the fingertip surface, but they cannot go as deep as OCT does. It's probably only 10 or 20 micrometers. Nevertheless, they still see some sort of improvement. So we hope to see even large improvement with our technology. So we use now Michelson interferometer, not the Linux interferometer, and we had a specially designed camera for these kinds of experiments, and a powerful LED. Now resolution drops to 20 micrometers or so, but we have a much larger field of view. This is a benchtop setup that I built, and these are images resolved in Z. So you start seeing sweat ducts, and then you run into internal fingerprint at some point. You can group these two layers, these images in 3 layers, as shown here in zoomed in version. So sweat duct layer, followed by internal fingerprint, and then a bottom of internal fingerprint where you see some sort of contrast inversion. You can compare side by side. Of course, they all the same because remember, external one regrows from internal one. You see sweat ducts here displayed nicely, and the thing to be said about it is that they also can be used for identification purposes. We're actually working on that with specialists in that field to try and use sweat ducts for identification, because that's a routine practice anyway in forensics. But we were wondering if we can resolve them better just looking below the surface, if that enhances the procedure. You can also see the fingerprint pattern here, which has some consequences. Basically, I don't have to go and image internal fingerprint, which might be somewhat deeper. And also you have to remember that, well, I didn't say that yet, but internal fingerprint changes from person to person and from finger to finger. So you don't know at which position it is, so you have to scan. But you don't have to really scan for it, because in epidermis there is also a fingerprint pattern. So here is shown a cross-sectional image. So you see an internal fingerprint, and then you also see in stratum corneum there's these lines which correspond to valleys in external fingerprint. So I don't have to go all the way down to internal fingerprint. If I'm not lucky, I just could image somewhere in between and still capture the fingerprint. So basically, by acquiring 2 images in 0.3 seconds, I was able to demonstrate that the fingerprint matching accuracy is quite high, 99%. I did that by tested on the almost 500 fingers. This was just a proof of concept that it works, that you can use internal fingerprints for imaging, for recognizing people. So I did that with this study. Of course, that's not the point of all the project. And the point is that when external fingerprint has some damages, we might not see that on internal fingerprint. Here's an exaggerated somehow an example where you delete external fingerprint, let's say with a sandpaper, but your internal fingerprint stays intact. You actually start bleeding, but still internal fingerprint is there. It's actually a technique practiced by some people when they get arrested and they want to escape being identified. Here's an example when you have a moisture on your finger. Again, it compromises surface quality somehow, but internal fingerprint is more or less unaffected. This is an old image. It doesn't look as good as it could probably. If you go below the internal fingerprint, you start seeing blood vessels. You start imaging blood capillaries, which also could be used in biometrics because this could be used as liveness detection. So sometimes in biometrics, in companies that make those devices, they try to come up with different solutions for liveness detection to see if a person didn't bring a dead finger or something of another person. It happened actually before. This is a portable version. The problem that we have a lot of specular reflections because we put a finger against the window. So we have 3 orders of magnitude higher intensity on the surface than on internal fingerprint. So we tried implementing dark field detection. This is shown in a high resolution system to get rid of the external information because we're not interested, and it actually uses the bandwidth of our camera. So we were putting a block in it, and we just re-imaged the pupil plane of the objective on a more convenient plane. And we used a grating rather than a mirror because we needed to get the reference beam around this block. Otherwise, it gives images at a tilted angle. It disperses also some light in the pupil plane, but that's not a problem. And just a demonstration that surface images might look a little bit odd, but if you go deeper in tissue, you see there's no difference. The only difference is that you see the first slide in regular imaging. It is basically saturated. However, we started running out of LED power. We used the most powerful LED we could, but we couldn't operate equipment in an optimal regime. So we came up with a new configuration that relies on 1090 beam splitter, and it allowed to send us more light and collect more light onto the camera. We used a small mirror put in a pupil plane that allowed to inject the light into the system, but the scattered light, which is a signal, goes around that block. So this is around that mirror. These are examples of images that you can acquire when you progressively go deeper. And as I said, these are acquired at an angle because I didn't use the grating here, but a tilted mirror. If you look from the side, you can also see axial images. There's a lot of things happening there. You see external fingerprint, internal fingerprint, and some capillaries going up, some blood activity. It's also good for any other part of the body, like skin. You can image skin. For example, you see dermis-epidermis junction here, live cells, dead cells. It's a stratum corneum here. So it could be used for many different applications. Another thing, I can image through surgical gloves here. So you see internal fingerprint, sweat ducts, and this is glove information actually also coming at an angle. And this could be used as a spoof detection, for example. So just to summarize, full field OCT can be used in biometrics in very different ways, from internal fingerprint imaging to spoof detection to liveness detection. And it's more suited to what we want to do because standard OCT acquires images fast, but they are cross-sectional. And we want fast and fast images. So I think I'm running out of time. This is acknowledgement to Gary Turney and Claude Boucoura, in whose labs I acquired these data. And thank you.
Ačiū pranešėjai Egidijai. Galim klausimus užduoti lietuviškai ar angliškai. Turim laiko vienam klausimui.
Prancūziškai.
Gal galit tada, aš užduosiu lietuviškai, rezoliucija, kas riboja fizinius mechanizmus, vadinama ta plokštumoji rezoliucija ir į gylį, lateral extra.
Tai dabar su ta paskutinė technologija, su OCT, tai rezoliucija yra ribojama, įdomiausia yra rezoliucija į Z einant. Tai čia yra ribojama šviesos koherentiniu ilgiu. Tai jeigu aš naudosiu platų spektrą, tai gausiu labai gerą rezoliuciją ir ji bus neribota objektyvo parametrais, kas yra šiaip ribojama, jeigu naudojant klasikinę mikroskopiją. Čia buvo rezoliucija 10 mikrometrų, bet mes tokią panašią ir gautumėm, 10 mikrometrų, tai yra izotropinė maždaug rezoliucija tiek platumoje, tiek į gylį, o šiaip būtų į gylį 1 milimetras kažkur, jeigu naudoti be koherentinio geitinimo.
Sekantis pranešimas